we have a function g, which is a continuous function from C to R, that is invariant under complex conjugation, so g of z is equal to g of z bar, and that g of z has asymptotic log of absolute value of z plus a small o of log of absolute value of z when z goes to infinity. And then we define a height associated to this function. For every alpha inside U bar, we take the minimal polynomial. P alpha is the minimal polynomial. And P alpha will be something like AD x to the d plus A0. And then the height associated to the function g of the number alpha is 1 over d, the degree of the minimal polynomial, times the logarithm of the main term, that is always assumed to be positive to fix the minimal polynomial, plus the sum for all beta inside the complex zeros of the polynomial P alpha of the function g evaluated at beta. So the height of an algebraic point associated with the function g has something to do with the denominator of the number, so the leading coefficient of the minimal polynomial, and then the average of the values of g for the different conjugates of alpha. And in particular, for instance, we saw that we recover the Wiles height if we put the function g equal to log plus. And then the problem is to compute the lim inf for all alpha inside Q bar of this function h of g. So we want to look at what is the smallest possible accumulation point of the values of the height, or so this will be the main problem, which is what we call the essential minimum of the height. And if you want, you can also ask for the absolute minimum of the height, but we will see that this is of h of alpha for all alpha inside Q bar. And we will see that this problem is slightly easier than the previous one. Okay. Now, let's start with an easy case example. Maybe we can also look at a slightly different problem. If instead of having an algebraic number, I look at an algebraic integer, the difference will be that the minimal polynomial will be monic. If the minimal polynomial is monic, then log of AD will be 0, this disappears, and then I get an easier constant. So if alpha belongs to ZD, to the set of algebraic integers, then h of alpha is just 1 over d, and then the sum for beta inside, let's call it the orbit of alpha of g of beta. So it's the average value of the function of on the conjugates of alpha. And then one can define the integral essential minimum of the height function just as the lim inf or alpha inside Z bar of this h g of alpha. So it's exactly the same problem, but instead of looking at all possible algebraic numbers, I only look at integral algebraic integers. And then one can ask, okay, what is the value of this guy? Or in general, whether this guy and this guy have the same value or not, or there is a big difference. No, so this can be extended to other settings, but in this course, I will only talk about the height of algebraic numbers, because the problem is just to determine this quantity. We'll see that is interesting enough to fix this. Of course, everything can be generalized to many other heights and can be done. But for the moment, I will only talk in this talk about the height points, point values. Of course, there are many other heights where you will be able to apply the same things. Okay, let's look at the first example, the Wiles height. So the Wiles height, the function is the function g is log plus, and log plus is positive. So what we see is that so w is the function g is log plus, and then we see that hg of alpha in this case is always bigger or equal than 0. And we know that the hg, for instance, of the point 0 is exactly equal to 0. So we know that the absolute minimum of the height of g is equal to 0, and the essential minimum in principle may be bigger. But we also know that if alpha to the n is equal to 1, so alpha is a root of unity, then height of alpha, height g of alpha is also equal to 0, which means that I have an infinite set of numbers whose height is 0, which in particular implies that the inf has to be 0, so the essential minimum of h of alpha is equal to 0. So this is the easy case. So for the Wiles height, the absolute minimum and the essential minimum are both equal to 0. Let's now go to the Frobenius to the height. G will be the log of 1 plus absolute value of z to the square, and then 1/2. Okay. Now, what we can see is that, again, the height g will be bigger or equal than 0 for everybody, because, again, this function is positive. So this value is always positive. And also, hg of the point 0 is, again, equal to 0. So we, again, obtain that the absolute minimum of hg is equal to 0. But now, if I look, for instance, to roots of unity, so if let's say, if alpha to the n is equal to 1, in particular, this implies that the absolute value of alpha has to be 1, and the absolute value of beta has to be 1 for all beta inside the sets of conjugates of alpha. So now the value here, if the absolute value of z is 1, I get 1 plus 1 is 2, so log of 2 divided by 2. And then the height of alpha is log of 2 divided by 2. So I get an infinite set of numbers whose height is log of 2 divided by 2. So for the moment, the only thing I can say is that 0 is smaller or equal than the essential minimum of this hg, and this is smaller or equal than log 2 over. Okay. And you can see that finding the essential minimum, in some sense, is difficult because you truly need an infinity of points converging to this quantity, not just a single point having this value. Okay, so how can we handle now the problem of determining what is the essential minimum? Well, whenever you have a number like this and you want to get estimates, usually what you do is to look for lower bounds and to look for upper bounds, and then hope that the upper and lower bounds are close together, so then you got a good grasp about the essential minimum. So now the next task is look for lower bounds. Then the good thing about the lower bounds is that they are easy to obtain, and the lower bound is based in one of the most important results or the most important tools in number theory that says the following: if I have set an integer which is non-zero, and maybe I take it positive, just to fix ideas, then I can compute the log of z, and this will always be bigger than 0. Okay. And it's curious that this principle is at the root of many theorems in number theory. And let's see how we can use this theorem to prove lower bounds for the essential minimum. No, because I am taking, sorry. Bigger or equal than 0. And if I subtract 1, then it will be strictly bigger than. Sorry. Okay, so let's look at the following lemma. Let's take Q, any polynomial with integral coefficients, and R, a positive real number. Then I can look at the function g of z minus R times the log of the absolute value of Q evaluated at the point Z. Okay, construct a new auxiliary function different from the previous one. And then I can look at the infimum for all elements in C of this function here and call it E. So remember I had my function G that was continuous and has this asymptotic. You can see that if it is continuous on C and has this asymptotic, this means that it goes to plus infinity when you approach infinity, and it has to be bounded below. It cannot go to minus infinity because it is continuous on the whole C. And now I am tweaking my function a little bit with this log of a polynomial, and then I can look at the infimum. Now this infimum can be minus infinity, but what is true is that for all alpha that are not in the zeros of Q, so for every alpha that is not a root of the auxiliary polynomial Q, the height of alpha is always bigger or equal than this quantity E. And in particular, since I am only taking out a finite number of possible elements, the essential minimum of AG has to be bigger or equal than this quantity E. Okay? So this is automatically a lower bound for the essential minimum. Whenever I have an integral polynomial and a number, and I tweak this function, and I look at the minimal value of the function, this will automatically give me a lower bound of the essential minimum, because for every alpha different from that is not in the zeros of Q, the height of alpha has to be bigger than this one. Let's see this result. So let's prove this result. So the idea first is to study the sum for all beta inside O of alpha. So let's say that alpha is an element that is not on the set of zeros of Q. Now I look at all the conjugates of alpha of the quantity log of Q of beta in absolute value plus, and then AD of, the degree of Q log of AD. Always AD will be the leading coefficient of the minimal polynomial of alpha. Now, this quantity, since it is full of logarithm, I can put everything together. This is just the logarithm of AD to the power D of Q times the product for all beta inside the zeros of P alpha of Q evaluated at the point beta, and then absolute value of everything. Okay? Now I have one polynomial evaluated at the roots of another polynomial, and then I make the product of all of them, and then I just fix by the leading coefficient of this term. Well, this is a very well-known quantity. This is exactly the resultant of P alpha and Q. Okay? But P alpha and Q are polynomials with integer coefficients, and they are coprime, because alpha is not in the zeros of Q. So this element is an integer, and is different from 0. And since I am taking absolute values here, it is a positive number, so the logarithm is positive. So you see I am using exactly this principle here. Okay? So this quantity is always positive. Now let's compute the height of alpha. Hg of alpha, this is equal to 1 over d log of AD plus the sum for beta inside O of P alpha, of alpha, of G of beta. Now, since this quantity is positive, and I start with this quantity, then this will be bigger or equal than the same quantity minus this one. I can subtract a positive thing to get something smaller. So this will be 1 over D of then log of AD plus the sum for beta belonging to O of alpha of G of beta minus R dq log of AD minus R sum for beta belonging to O of alpha of G of beta. I am using the fact that my number R is positive and this quantity is positive, so I am subtracting a positive quantity. Okay, sorry? Yes. Log of absolute value of Q. Yeah, the quantity I want to subtract is this one. Perfect. Now let's rearrange the terms. So this is 1 over D. Then log of AD, I have the quantity is 1 minus R dq divided by this times log of AD plus, and then I have 1 over D, the average of the sum for beta inside O of alpha of G of beta minus R log of absolute value of Q evaluated by beta. Okay, just have arranged some terms. Now there are two cases. Let's go, yeah. Maybe I can at least this one that I have used it already. Now I can distinguish two cases depending on whether this coefficient is positive or negative. So if R dq is smaller or equal than 1, then this quantity is positive. And so I can neglect it. I get that Hg of alpha will be bigger or equal than what remains here, 1 over D, the sum for all beta inside of alpha of G of beta minus R times log of absolute value of Q of beta. So the height of alpha is bigger than the average of this function on the conjugates of beta. But of course, E was the infimum of this function. So the average value is always bigger than the infimum. So this is bigger or equal than E. What happens if R times dq is negative? No, it's bigger than 1, sorry. What happens if R dq is bigger than 1? Then this is the trivial case because, let's go to the assumptions. The function g behaves like log of z. Now my polynomial q has degree dq. If R times dq is strictly bigger than 1, this means that log R times log of q is so it's bigger than log of z. But not just bigger, it's much, much bigger. I mean, let's say, log of z is a small o of this quantity here. Hence, in this case, this quantity grows much faster than this one. But since I am subtracting it, this means that this infimum has to be minus infinity. So in this case, E is equal to minus infinity. And of course, E will be smaller or equal than h of alpha. Because it's a real number, this is minus infinity. So we still have the inequality. So in any case, we have that for every alpha that is not in the series of Q, the height of alpha is bigger or equal than epsilon, than E, and hence the essential minimum is bigger or equal than E. Okay. Is clear this? The good thing is that this is not only useful to get a lower bound for the absolute minimum, for the essential minimum, but it will also make very simple the determination of the absolute minimum. Because now, if there exists a pair RQ such that the corresponding E is bigger than H of alpha for some alpha inside the series of Q, this may happen. So here what I am proving is that for every alpha that is not a series of Q, the height is bigger than E. But it might perfectly happen that one of the series of alpha has height smaller than E. Then what we know is that the absolute minimum of the height G will be exactly the minimum of H of alpha for all alpha inside the series of Q. The moment there is one element that is below this lower bound, there will be only a finite set of guys below this lower bound. And since it's a finite set, finding the infimum is just you look at all of them, look at the value, and you get the infimum. Okay? So this gives me a lower bound and also an easy way to understand what can be the absolute minimum. Of course, the difficulty is to find this polynomial. I mean, maybe this polynomial is very easy to find, but we don't know which one is it. Is this clear? Okay, now let's apply this to the Fubini study. Okay, so in the Fubini study case, we have that the height of the point 0 is 0, which is exactly the absolute minimum. And maybe since after trying a lot, we have not been able to find any other algebraic number whose height is close to 0, we might think, oh, maybe the absolute height is bigger, the essential minimum is bigger than 0. For instance, can be this quantity if the roots of unity converge to the minimal value. Which means that if I want to apply this result, observe that I need a polynomial such that all the elements with a small height have to be zeros of this polynomial. I have an element which is the element 0 that I know that has very small height. So since I want to take it out, I need to use at least a polynomial that vanishes at 0. Well, the easiest polynomial that vanishes at 0 is the polynomial x. So let's take q equal to x. So the zeros of q is just the set 0. And then I look at the function g of Fubini study minus, and then, of course, one can start looking at possible values of R. One has to make an optimization process, so to look at the infimum of this function, and then the supremum for all R's to get the best result. But let's try just R equal to 1/2, minus 1/2 of log of absolute value of z. Okay, so this function is just 1/2 of log of 1 plus absolute value of z divided by absolute value of z. And then I can look at the infimum of this function. Z square, and this, this is, so this is the function. Yes. And then I am looking at the infimum of this. Okay. And now the infimum of this phi, well, now you use your undergraduate tools, you look the infimum of this function, and you show that this infimum is exactly the value at the point 1. And it is exactly equal to 1/2 of log of 2. So we get now that the essential minimum of this H Fubini study is exactly equal to log 2 divided by 2. Okay. So in this case, the easy lower bound automatically gives us the absolute. Okay, so there is no wonder because this Fubini study height satisfies that historic. So this G Fubini study historic, which means that G Fubini study of any value set is exactly equal to GFS of the absolute value set. So it has this rotational symmetry. And then if you have rotational symmetry, then one can compute the essential minimum, the absolute minimum, all the successive minima are very easy to compute. And in fact, there is a paper in the literature that shows how to compute everything. And we have seen that in this particular case, it was very easy to compute. But in other situations, things can be much more difficult. Questions now? Okay. Because it corresponds to the usual L2 norm. And then if you look at the bundle of one and you put the standard metric that gives you the Fubini to the volume form, is exactly this metric. And these kind of metrics are called Fubini study because they come from the standard metric. So it's the standard metric you put on the projective space coming from the standard. Okay. Now, there are two things that we can say. Okay, here we have written this lemma for a single polynomial. But you can imagine that I can use, instead of one polynomial, one can use many polynomials. So I have the following variant. I can look at Q1 up to Qn polynomials or Q sub k polynomials in set of X and R1 up to Rk, 0 to 0, real numbers. And I can look at E equal now to the infimum for set inside C of G of set minus the sum I equal to 1 up to K of Ri log of absolute value of Qi of set. Okay. Instead of just subtracting a polynomial, I can subtract a lot of polynomials, and this is again smaller or equal than the essential minimum of H. Okay. So this is not very strange because in some sense I can always assume that the Ri's are rational numbers because I can approach any lower boundary by rational numbers. And then if they are rational numbers, I just can pack together all the polynomials in a single polynomial. So using this result and the density of the rational numbers inside the real numbers, we can get also this result easily. Okay? And sometimes this is easier to use. Okay? This is and then the second observation is that these lower bounds are sharp. In the following sense. The family of lower bounds is sharp. There is a theorem that is due to Valais in the case that G is what is called plurisoharmonic, so some positivity is needed, and then to Q and Gin in the general case, that tells me that the essential minimum of Hg is equal to the supremum for all Q inside set of X and all R bigger or equal than 0 of the infimum for all set belonging to C of G of set minus R log of absolute value of Q of set. Okay. So that if I look at all these possible lower bounds and I look at the supremum of all possible lower bounds, I exactly get the essential minimum. Okay. This theorem is valid not just for P1 and this kind of heights, but this is valid for any variety and any height function. So the essential minimum is always attained as the supremum of this kind of lower bounds. Okay. Which in some sense is a good thing because this means that the essential minimum maybe can be approximated as much as you want, because you start looking at these lower bounds. Then the family of polynomials with integral coefficients is countable, so maybe you can order them and then put a computer that starts with the first polynomial and go on, and maybe before the sun goes down, we will get a very good approximation of the essential minimum. No, it's not a maximum, it's only the supremum. In the theory case, it's a maximum, in general, it's a supremum. But here we have a problem, is that we only have lower bounds. And for the moment, we don't have any idea of how close we are to the true value. And maybe we spend thousands of years below some threshold, and then suddenly we find a polynomial that gives us a leap going up. I mean, we know that eventually we will approach the value, but we don't have any idea of what will be. So lower bounds are very nice, but they are not enough because they don't give us any idea of how close we are to our result. So now what we will need are upper bounds. Then the lower bounds, as we have seen, are very easy. So they are based in this principle that the logarithm of a non-zero integer is always positive. But upper bounds will need much deeper results to be possible to. And so before entering to discuss upper bounds, I want to discuss the principle of equidistribution of small points. So the equidistribution principle is behind the proof by Ulmo and by Zhang of Bogomolov conjecture, and has many, many variants and has been used in many situations, and says the following. So equidistribution principle. Okay. So imagine that I have X, a variety defined, for instance, over Q, and H, a suitable height function. Okay. Now imagine that I have a sequence alpha n for n bigger or equal than 1 of points. Alpha n are points in X of Q bar. So they are algebraic points, such that they satisfy two conditions. The first condition is that it is what we can call generic. This means that the set for every y inside X, but that is not X, so always X will be irreducible. So always my varieties, I will think then of being irreducible. So generic means that for every y, a proper subvariety, which is not the whole variety, the set of n's such that alpha n belongs to y, this has to be finite. So I don't want my sequence to accumulate in a subvariety. So I want it to move a lot. So this is called generic. And the second condition is to be small. And to be small means that if I look at the height of the alpha n, I want that this converge when n goes to infinity to the minimal possible value. And what is this minimal possible value? So if the sequence is generic, means that it moves. Hence, the minimal possible value of a limit of a generic sequence is exactly the essential minimum of H of the height function. So the any generic sequence, the minimal possible value that its limits can have is the essential minimum. So I assume that I have a sequence that is generic and the height of the points converges to the minimal possible value. Then the equidistribution principle tells me that then the orbits O of alpha n, so these are finite sets, should converge . to a fixed shape. Okay. So I have to apologize because I had a nice program to illustrate this principle, but in the last upgrade, it crashes. So I have maybe next Thursday I will be able to show you how this principle works. But the idea is that if I have a sequence that is generic and small, I look at the Galois orbits of the elements in the sequence, and these Galois orbits, these are a finite set of points, and this finite set of points should converge to some shape. Now you can imagine, for instance, that you have, I don't know, 3 points like this. Then in the next sequence, you have that the orbit is something like this. Maybe one point is very far, but most of the points are this. And then you are willing to say, okay, if I have this shape, what is going on? That the orbit should converge to the unit circle. Now, this will be more or less the idea of these shape. Okay. Now, some remarks are in order. First is that I am saying equidistinction principle, and here I am not saying that it converges. I am saying that it should converge. The problem is that, in general, it depends on H. So, for instance, in the bibliography, you have a theorem of Yuan that is one of the most general equidistribution results that exist. That remember that we had this inequality that says that the essential minimum was always bigger or equal than the height of X. Then there is a theorem that if we are lucky and these two guys are equal, then the equidistribution principle holds. But in general, it's not clear whether it will hold or not. And for instance, in the literature, you will find also a paper that in the case of toric varieties, that things are easier to check, it checks when it holds. So there is an if and only if. So if the metric satisfies certain conditions, you have equidistribution. If not, you don't have equidistribution. So it's a principle and not a theorem. Okay. Well, this is the third the third comment. Okay. So the first comment is that it's a principle because it does not always hold, but sometimes it holds. The second thing is this idea that the minimal possible value is the essential minimum. And then the third comment is, what does it mean? Thanks for the question. What does it mean to converge to a fixed shape? I mean, shapes don't converge. So we need to go to a place where I can talk about a topology and I can talk about a limit thing. So then what I can do is that whenever I have a finite set, like this orbit, I can always define a counting measure. So given a finite set, O of alpha, I can associate, or to every finite set. We can associate a counting measure. Delta of O of alpha, which can be seen, can be written as 1 over the number of elements in O of alpha of the sum for all beta inside O of alpha of the Dirac delta at the point beta. Okay, what does it mean? So typically when you have a measure, and let's say a radon measure, what you do with a measure, you integrate continuous functions. So what does this mean? This means that the f is continuous, then the integral of f d of this counting measure is just 1 over the number of elements in the counting measure, and then the sum from beta inside this set of the value of the function at the point beta. It's clear? So this is how I can transfer a finite set to a measure, just by the counting measure that when I evaluate in a function is just taking the average of the value of the function on the elements in the set. Okay? And this is a probability measure. But now the space of measures is a topological space. So now I can start making a precise meaning. What does it mean that this converges to something? So that the fact that it converges to some shape. So this means that there exists a mu, a measure, such that the limit when n goes to infinity of delta of alpha is just this measure mu. Okay? Well, but now you can complain because the space of measures is an infinite dimensional space. If we are in a finite dimensional vector space, then everybody agrees about the topology. If you are in an infinite dimensional space, nobody agrees in the topology. You can have a different topology for every person in the audience. In particular, because these measures, I am taking them on C, not on P1. So I am taking measures in a non-compact space. And I mean, if we were in a compact space, maybe more people will agree. What does it mean, measures to converge? If I am in a non-compact space, it's even more difficult to define what does it mean to converge. So let's make a definition of 3 different notions of convergence. So let's mu n for n bigger or equal than 1 be a sequence of measures. Okay. And mu on C and mu a measure on C. Okay, I have a sequence of measures and a measure on C, and I want to say what does it mean that the sequence converges. Then the first part is we will say that mu n converges to mu weakly. Okay. So the key point here is weakly. If for every a function f from C to R continuous and bounded, I have that the limit of the integral of f d of mu n is equal to the integral of f d of mu. Okay, so we'll say that. No. Well, that's the point. So I will say that this weakly converges if this happens for every bounded continuous and bounded function. Then I will say that it converges weakly. It's a definition. Why not? The second condition is that I will say that mu n converges to mu logarithmically if and only if for every f from C to R that is continuous and satisfies that f of z is smaller or equal than a plus b log plus of z for some bigger or equal than 0, the same condition holds. Lim when n goes to infinity of the integral of f d mu n is equal to the integral of f d mu. Okay, so this is another definition. So this is that we say that converge weakly if we have convergence for every continuous and bounded functions. We'll say that it converges logarithmically if we have convergence for every function that is continuous but not even bounded. So it's bounded only for the log. And the third condition, the third definition is that we say that mu n converges to mu properly if and only if for every f from C to R continuous, the limit when the integral of, so the limit of the integral of f d mu n is the integral of f d mu. So we will say that we have proper convergence if we have convergence for every continuous function. Okay, so we have 3 different notions of convergence. And since C is not compact, then they are different. If I were working in a compact space, they will be the same. And now, going to the question of Jacques, is that 3 is equivalent to 1 plus the fact that there exists a compact K says that the support of mu and the support of mu n for all n bigger or equal than a threshold n0 are all contained in K. Okay, so this is the typical convergence for things with compact support. You need a common compact support, and then you need convergence. But in some sense, this convergence is too strong, and sometimes you don't have this convergence. So in general, the equidistribution principle only gives you weak convergence. Okay. And then why I have these 3 conditions is that, in some sense, what we will desire will be to have proper convergence, because proper convergence will give us convergence for any continuous functions. But this is just daydreaming. In general, if you don't have that everything is inside a compact, you will never have proper convergence. Now, logarithmic convergence is the important one for us because my function g, that is the one that I am tested, the function that gives the height, is a logarithmic function, satisfies this bound. And then if I have logarithmic convergence, I will have convergence of heights. Okay? But the problem is that, in general, the equidistribution principle gives me only weakly convergence, which means that there is no convergence of heights, which means that I am in trouble. So I will have, at some point, to discuss about these 3 convergences, what kind of convergence do we have. Okay? But it is clear. What does it mean that a sequence of measures converge, and then the equidistribution principle will say that, so for instance, in this example, what we will have is that the limit of delta of O of alpha n will be equal to the hard measure on the unit circle S1. And typically, what will happen is that most of the points are on the circle, but there are sometimes a point that is very far away. And this will ruin proper convergence, and this will ruin logarithmic convergence. So the only convergence one has is weak convergence because of these outliers that can be very bad. Questions about what is the equidistribution principle? It's clear. Perfect. So now we can start developing the theory needed for the upper bounds. Okay? Yes. Yes. Exactly. Exactly. So typically, so for instance, in this case, I have the circle and the hard measure on the circle. Here it's clear that the shape is the circle and then the measure is the unit circle. In general, by a shape, I mean a measure. Typically, this measure will be the equilibrium measure of some compact. So in some sense, it will have some geometric content. But in general, the only thing that you can say is that it converges to a measure. And then by abuse of notation, say that a shape is a measure. So the problem is that in order to get convergence, you need to go to a very flexible place where you have all the limits you want to consider. Okay. Upper bounds. Now for upper bounds, as I was saying, the lower bounds were easy or cheap. The upper bounds, they all need some theory. And then to discuss upper bounds, I will need a crash course in potential theory. Okay. Then I start with P of C. This will be the probability measures on the complex plane C. And then I will define P log of C. This will be the probability measures. It's a subset of P of C, such that the integral of log plus of absolute value of set D of mu is finite. So I want to look at probability measures such that the integral of log is a finite quantity. So this will be the probability measures. Now, whenever I have an element mu inside P log of C, I can define the potential. The potential U of mu is equal to the integral of minus log of set, so the potential and the variable set will be minus log of set minus W d mu of W. Okay, so the potential is defined as the integral of the function log of d of set minus W d mu of W. Okay. Now the problem with this integral is that the function log has two kinds of singularities. On one hand, if the difference is very big, then this will go to plus infinity. Since I have a minus here, it will go to minus infinity. On the other hand, if these two guys are very close together, then this goes to 0, the logarithm will go to minus infinity, and with the minus sign, it will go to plus infinity. Now, when we have an integral that can go to plus infinity and minus infinity, you have no clue what is the value. It can be undetermined because you have these two quantities. But since we assume that my measure is in P log, I know that the integral of the logarithmic singularity is finite. Which means that of the two singularities, the plus infinity singularity and the minus infinity singularity, one of them will not show up. So when this guy goes to 0, this will appear, but the other one will not show up, which means that this integral is well defined. So I don't have problems of it being not well defined. The other thing is that it's well defined, but maybe not finite. But at least it is well defined. So this is an element in R union plus infinity. But it's well defined. So it might not happen that I have plus and minus infinity. Okay? And in general, this will be a function that is locally integrable. So U mu is locally integrable. And in fact, one can recover the measure mu as 1 over 2 pi I, no, 1 over 4 pi I, then delta delta bar. So this is the anti-holomorphic derivative and the holomorphic derivative of the function u mu. So in some sense, from the measure we can get a potential, and from the potential we can get a measure. And the reason I restrict to the log measures is that in some sense this is the bigger space where potential theory can be done. In general, in the elementary books on potential theory, people restrict to measures with compact support, and then everything is fine. But in general, you can extend to functions with logarithmic growth. Okay. Now this is the potential, and now the energy of my measure is the integral along C of the potential u mu d of mu. Or if you want, this will be a double integral of minus log of absolute value of W minus Z, d of mu W, du of mu. So this is the potential of mu. And then this is the d and d bar. This is the anti-holomorphic derivative and the holomorphic derivative. So you can think that this is a 1-1 form on P1 that you can assimilate to a volume form, and then is equal to the measure as a volume form. Yeah, thanks for the question. Okay, and then I can define the energy of the measure as this double integral, and this is again an element that can be in E in R union infinity. Okay. Now, in some sense, the idea of this comes from physics and comes from electrostatic potential or gravity, in the sense that we can imagine that my measure is telling me the distribution of a lot of particles with a charge, and that the force between these particles has a potential which is of the logarithmic shape. And then this double integral will tell me what is the energy that these particles have. And then if they get more separated, I will get less energy. If they get concentrated, I will get more energy. Okay, and this is more or less the idea of this potential theory. So the important thing is that I have an energy associated to this quantity. Now, assume that I have a compact. So let K be a compact set. And now what I want is to confine my particles in this compact set. So imagine that now instead of having particles that lives in the space and can be separated as much as I want, I have just a conductor, a circle for instance, and I put my particles there so they cannot go to infinity. They can try to separate as much as possible, but remain confined in this set. And then I can look at the energy of this compact set, and this will be the infimum of the energies of mu for all mu, the infimum for all mu with support. The subpart of mu is contained in K. So I can look at all possible distributions of particles inside my fixed set, and I can look at when the energy is as small as possible. And this will be the energy of my set, okay? So for instance, if I am in a sphere, the particles will try to be as separated as possible among them, and possibly they will get equidistributed on the sphere, okay? And then I can define the capacity of my set K. Well, this is just the same as the energy, but with a small difference. This will be E to minus E of K, okay? So you see, this is just, in some sense, pure physics in a two-dimensional space, in P1. But what is very funny is that it has a lot of arithmetic implications, okay? So let's see what are the arithmetic implications here. So now a notation. I will write if epsilon is bigger than 0 and K is a compact, I will write B epsilon of K. This will be just the set of X inside C, such that the distance between X and some point of K is smaller than epsilon. Okay, so this is just an epsilon neighborhood of my compact set K. Okay? And then we have the theorem by Fekete-Sego, that tells me the following thing. So if I have K inside C, a compact set, and which is invariant under complex conjugation, so I need that K is equal to K bar in the sense of complex conjugation, then I have a dichotomy. Either the capacity of K is strictly smaller than 1, and if the capacity of K is strictly smaller than 1, then there exists an epsilon bigger than 0, such that the set of alpha inside Z bar, the set of algebraic integers with the property that the whole Galois orbit of alpha is contained in this small epsilon neighborhood of K, this set is finite. Okay? But if the capacity of K is bigger or equal than 1, then for all epsilon bigger than 0, the set of alpha inside Z bar, such that the whole Galois orbit is contained in the epsilon neighborhood of K, this is infinite. Okay, so the capacity of a set is telling you whether you have or not a lot of integers that whose Galois orbit is completely contained in a small neighborhood of your set. Okay, a very arithmetic application. If your set is very small, you will not be able to find many integers. If your set is big enough, you will be able to find a lot of integers. Now, for instance, if I look at a circle, so let's look at a circle. If I look at the circle of radius strictly smaller than 1, no, for instance, this is 0, this is the point 1. I look at a circle smaller than 1. If I look at integers whose orbit is completely contained in the set, there is only one, which is 0. So the set of elements is bounded. Okay? So this is clear because if you have integers, the product of the norms of all of them has to be 1 because, so there is I don't remember now the argument, but it's very easy to prove that if the circle has radius smaller than 1, the set of algebraic integers that the whole orbit is contained in the circle is finite. But the moment we reach 1, now I have all the roots of unity. Hence, I have an infinite number of integers. Well, for this circle is very easy. But imagine that you start with a circle centered at P. Okay? With this theorem is telling you that if you take the circle of radius smaller than 1 around pi, you will only find maybe none, maybe finite number of integers whose closure is exactly contained in this circle. But if the radius is exactly 1 or bigger, well, you don't know whether you will have a lot of integers, because since you are displacing by pi, this destroys algebraicity. But what it's telling you is that the moment you make it slightly bigger, you make a small epsilon neighborhood, now you will find an infinity of integers that are contained in this circle. Exactly, and that's the point, that for a circle, the capacity of SR is exactly equal to R. It's almost the only case where you can make all the computations easily and get the capacity. But for a cycle, the capacity is exactly the radius of the circle. Questions? Okay. Now, we have a little bit even more. So when we have a compact and we have this infimum, in this case, this is not an infimum, this is a minimum. So the good thing is that there exists a unique measure, mu of K, such that the energy of K is equal to the energy of this mu K, which in some sense is the distribution of the charges in this physics idea. So there is a unique solution to this problem. Okay, and then and now the point is the following. Observe that when I have a set of capacity bigger or equal than 1, so let's assume that I have K, a set of capacity 1. Okay. Now, for every n, we can find an alpha n such that the orbit of alpha n is contained in the ball of radius 1 over n, well, of the neighborhood of K of radius 1 over n. Because since there is an infinity, I can find a new one, and I can find this alpha n generic. So such that alpha n is different from alpha m for every n different from m. Okay, so in each stage, I avoid the previous one just to not to be. Now we can ask what is the limit when n goes to infinity of the counting measure of this alpha n. And then there is a theorem by Rumely that tells me that this limit exists and is exactly this measure mu k. Okay? So that if I have algebraic integers that are very close to my compact set k, then the Galois orbits of these integers converge exactly to what is called the equilibrium measure of k. Okay? So, and this is a very nice blending of arithmetic with physics and analysis, where in some sense you can predict the shape of the Galois orbits of the integers that are inside the set, and they will converge to the equilibrium measure. Questions? Yeah. So maybe it's time to stop here. Thank you.